Welcome back to this course on multi-core architectures. In the previous module, I have focused on centralized shared memory architectures in which coherence is maintained using a snooping cache coherence protocol. Such snooping protocols rely on a broadcast-based interconnect such as a bus. The problem is, however, that a bus does not scale. In this module, I will therefore describe a different kind of protocol called directory protocols that can support larger systems with more cores. This lesson is based on section 5.4 of the textbook. Some slides are also based on section 5.5 of the book Parallel Computer Organization and Design by my colleagues Michel Dubois, Murali Anavarim and Per Stenström. Before I start this lesson, a short recap of some limitations of snooping cache coherence protocols commonly used in symmetric multiprocessors. Snooping protocols rely on broadcast, since on a cache miss or write, all caches need to be informed. The natural broadcast medium is a bus, but unfortunately a bus does not scale well. This means that when more cores are added, its length and hence its latency increases. And furthermore, the bandwidth available per node decreases. So what can we do to increase the bandwidth? We should replace the bus by a scalable interconnect, such as a mesh, a two-dimensional grid. In addition, we should distribute the memory across the nodes so that each processor is directly connected to a piece of the shared memory, sometimes called its local memory. In such an organization, as shown here, the memory is distributed, which is why it is called a distributed shared memory system. Furthermore, in such a DSM system, an access to the local memory will be much faster than an access to a remote memory. For this reason, such systems are also called cache-coherent non-uniform memory access architectures, or CC-NUMA. Distributing the memory gains us little if every cache miss or write still needs to be broadcasted to all nodes, since then too many cache coherence messages need to be sent. The solution to this challenge is to employ a different kind of coherence protocol, different from snooping. This different type of coherence protocol is called a directory protocol. The directory keeps the sharing status of every block. It indicates which caches have a copy of the block, if it is dirty or modified, and maybe some other information. The example at the bottom here of this slide illustrates what the directory entry for a certain block B might look like. In this example, the directory entry indicates that both node 1 and node 3 both have a copy of this block, while node 1 and node 2 don't. I will now describe a basic directory protocol. This protocol is either called the full or presence flag factor protocol. On this slide, I show the same figure as before, a distributed shared memory system. First, we distribute the directory along with the memory as shown here in orange. Every piece of the directory consists of a number of directory entries, one for every memory block. Furthermore, every directory entry consists of capital P presence bit small pi, where capital P is the number of cores. If pi is set, that means if it equals 1, it indicates that the cache of processor I contains a copy of this block. In addition, there is one extra bit called the dirty bit, which indicates that the copy is dirty or equivalently modified. If this bit is set, exactly one presence flag pi can be set, since the block can be modified in only one node. To make it scalable, the directory is distributed along with the memory. This avoids that all coherence requests have to go to the same node. Furthermore, processor or node I contains all directory entries for the memory blocks that are mapped onto its part of the physical shared memory. This node is called the home node of those blocks. This ensures that the coherence protocols knows where to find the directory information for any cached memory block, since the identifier of the home node can be found during virtual to physical address translation. Up to 3 types of nodes can be involved in a coherence transaction. These are the local or requesting node, the node that makes the request, such as a read-miss. Second, the home node that I already described on the previous slide, the node where the memory block and the directory entry reside. And potentially remote nodes may also be involved. These are the nodes that contain a copy of the memory block. For example, these copies might need to be invalidated. To give you an idea how the directory protocol works, let me now illustrate the sequence of messages that need to be transferred between the participating nodes. Here we have a CC NUMA with 3 nodes. The local node that makes the request, the home node that contains the block and the directory entry in the middle, and the remote node on the right. As an example, I will consider a read-miss to a block that is dirty in a remote node. First, the local processor does a lookup in its private cache. The lookup will result in a miss. That's what we assumed. So a read-miss message will be sent to the home node, as I illustrate here. Then the home node checks the directory entry for the corresponding block. It finds that the block is dirty in the private cache of a remote node. So it replaces the read-miss by a remote read message and sends this message to the remote node like this, through the network. Upon receiving this message, the remote node does a cache lookup and answers with a reply message containing the block data as well as its address. In addition, it changes the state of its copy of the block from modified to shared. The reply message is sent back to the home node like this, and the home node now does 2 things. First, it writes back the block in its local memory so that the block is clean again and clears the corresponding dirty bit. And finally, it forwards the reply to the local node, which can now allocate its copy in state shared. This completes this lesson. Thanks for watching. In the next lesson, I will describe an example directory protocol called the Full Directory Protocol or Presence Flag Factor Protocol. Hope to see you back.